Let ABC be a regular triangle with side length 2 and P an arbitrary point inside the triangle. The distances from P to three sides BC, CA, and AB are P, Q, and R respectively. Question: calculate P plus Q plus R. I'm going to present two approaches. First, using areas of triangle, and second, using normal equations. I will compare their advantages and disadvantages. The easiest way is to use areas of triangles. We use brackets to denote areas of triangles. P and the three sides BC, CA, and AB form three smaller triangles PBC, PCA, and PAB. They sum up to the regular triangle ABC. Let's look at the areas. The base of the regular triangle ABC has a length 2, and the altitude is square root of 3. Therefore, the area of triangle ABC is square root of 3. You can use Pythagorean theorem to get the altitude of triangle ABC. On the other hand, for three smaller triangles, their base lengths are 2 as well. The altitudes are P, Q, and R respectively. If they sum up to square root of 3, we end up with an equality P plus Q plus R equals square root of 3. Is it enough? A natural question is that what if P is outside the triangle ABC? For example, if P is directly below the side BC, what would happen for those three altitudes P, Q, and R? Let's look at the four triangles. Now, PBC is outside the triangle ABC. So we have a negative area of PBC plus the area of PCA plus the area of PAB equals the area of ABC, which is square root of 3. By the definition of the three altitudes P, Q, and R, we can calculate the areas in terms of P, Q, and R. Simplified, we have a negative P plus Q plus R equals square root of 3. If the point P is directly below the side BC. Another scenario. If P is outside the corner of C, in this case, triangle PAB is the largest, covering all the other three triangles. In this case, we have a negative P minus Q plus R, which is the largest, equals the area of triangle ABC, square root of 3. The lines of three sides partition the plane into 7 regions. The relations for P, Q, and R are all different in each region. Inside the triangle, that's P plus Q plus R equals square root of 3. Below that, negative P plus Q plus R. The sign for P is changed. Move to the corner outside the C, the sign for Q is changed as well, negative P minus Q plus R. Move up to another region, the sign for P switch back from negative to positive, and so on. The signs for P, Q, and R can be either positive or negative. In theory, there are a total of 8 combinations. One of them is excluded in the picture. They cannot be all negative because area of the triangle ABC is positive. All other 7 combinations show up in the picture. So far, everything is easy and good. Here is a big question. What are these to do with normal form equations? Let's put the triangle in a rectangular system. The coordinate of A is 1 square root of 3, B as origin 0, 0, C 2, 0, and the P, the arbitrary point with coordinate x0, y0. You can easily check the side length of the triangle is all 2, and the area of the triangle is square root of 3. Now, let's establish the equations for 3 sides. We go BC first. The equation for BC is y equals 0, the x-axis. The normal form of the equation is exactly the same one, 0x plus 1y equals 0. So, because 0 squared plus 1 squared equals 1. If you are not familiar with normal form of linear equation, please watch my previous video. Now, let's use this normal equation to calculate the distance from P to BC. We plug in the coordinates x0, y0 in the equation, calculate the absolute value, and we are done. The question is that, can we remove the absolute value sign for y0? In this case, we already know one side of the line is positive, the other side is negative. And the P is on the positive side. So the distance P equals y0, which is positive. For this case, it's very easy to see. Let's look at another line for AC. That is not that simple. First, we calculate the slope for CA using 2 points A and C. The slope is negative square root of 3. And then we establish a point slope form equation using the point C to 0. Y minus 0 equals the slope negative square root of 3 times x minus 2. Rearrange the term, we got the standard equation, square root of 3x plus y equals 2 square root of 3. In order to normalize the equation, we calculate square root of 3 squared plus 1 squared. We have a 2 squared. So we need to divide by 2 from both sides of the equation to get the equation normalized. After we got the normalized equation, we can calculate the distance from P to AC by substitute x0, y0 in the equation, calculate the distance, and then, calculate the difference, and then take absolute value. Now the question again, is it positive or negative inside the absolute value sign? This is easy to test because the point P and the B 0, 0 are on the same side of the length AC. If we plug in the coordinate of B 0, 0 in the equation, we got negative. That means P and B are on the negative side of the equation. Therefore, when we plug in x0 and y0, the value must be negative. So, the distance q from P to AC is the negative of that quantity, which is positive. Similarly, we have equation for AB. That's easy. Y equals square root of 3. Normalize this by divide by 2 from both sides. We got square root of 3 divided by 2. X minus 1/2 x equals 0. You can test this time T is on the positive side of that equation. In other words, when we calculate the distance from P to AB, we simply plug in R equals whatever, square root of 3 divided by 2, x0 minus 1/2 y0, which is positive. Now, let's put everything together. When P is inside the triangle, we have the distance from P to BC, y0, and P to CA is this quantity, positive, and C to AB is R, also positive. Sum up, we have P plus Q plus R equals, this is P, Q, and R. Combine the like terms. You see the like term for x0, positive, negative, cancel out. For y0, 1, negative 1/2, negative 1/2, also cancel out. So we end up with square root of 3. Compared with the area method, this normal equation approach seems trickier. Are there any advantages of it? Let's look at the algebraic equality. This equality works for all real numbers x0 and y0, no matter where the point is, inside or outside the triangle. It is just algebra. What does that mean? Let's revisit the case for P directly below the side BC. Y0 is negative. The distance from P to BC is absolute value of y0, which is negative y0. Therefore, y0 equals the negative of the distance from P to side BC. Now, let's look at the equality. y0 plus q, the distance to CA plus R equals square root of 3. Now, y0 is negative P plus Q plus R equals square root of 3. This is exactly the same thing we discussed earlier. In other words, the same equality is perfectly consistent with the case where P is directly below or above the side of BC. Not only these two cases, as a matter of fact, this single equality can explain all the 7 cases. Next time, I'm going to discuss the application of normal linear equations on angle bisectors. Thank you for watching. Please consider subscription of my channel. I appreciate your support.